chemical, different types of chemical reactions we learned in 9th class. What they are: combination reaction, decomposition reaction, or double displacement, or displacement, right? Electrolysis process. So from that, here you need to just have an idea about a displacement reaction. What is displacement reaction here? One of the element is replaced by another element in the compound, right? So it is possible by the more reactive element only. More reactive element can replace least or less reactive element. More reactive element can replace least reactive element, right? So that type of reaction called as displacement reaction. Suppose here, if you observe the reaction between the magnesium and titanium, right? So magnesium is high reactive comparing with the titanium. So magnesium is more reactive, greater in reactive, right? Or top at the reactivity series comparing with the titanium. So here that magnesium will displace here titanium and it can form a magnesium chloride. The titanium will be separated here. Titanium will be separated. So using this simple reaction, you are able to extract least reactive metals, right? We are able to separate least reactive metals. So it is actually at high temperatures. The displacement reaction will be takes place at high temperatures. So these are called as thermal reactions or thermite process. So in this, what happens? Highly reactive metal can displace the least reactive metals, right? They are used as simply reducing agents to displace one of the particular metal, right? So simply they are exothermic reactions. They are called as here exothermic reactions. They can release high amount of energy while displacing. For example, the displacement reaction already we observed in a second lesson or in third lesson, zinc metal piece reaction with the acid. So here zinc is high reactive element comparing with hydrogen. It can displace hydrogen from HCl and forms zinc chloride and liberates hydrogen gas. Along with this, you will get something heat energy. So this is exothermic reaction. So displacement reaction is example for the exothermic reaction. So it can release high amount of energy. Due to that high amount of heat energy, that produced metal or displaced metal will be available in the molten state, liquid form, right? So using this type of reaction, just you are filling the gaps between the tracks in a railway tracks. They are using thermite reaction. So that reaction between iron oxide and aluminum, right? The reaction of iron oxide with aluminum produces molten iron. Molten iron. So here simply this iron which is available in the liquid form will be used to fill the gap between the tracks. Here look at. The gap is filled by molten iron. Then it will be just what is adjusted, right? What is smooth and soft and whatever it means, cutting extra material, right? So leveling, the gap is filled and leveled. So this is called a thermite reaction. This thermite reaction will help you to fill the gap of joining railings, right? Like a welding, right? So this process will help us. So this is about a thermite reaction. Remember the equations, compulsory. right? Iron oxide converted into iron. Here, aluminum is at a high reactive series and iron is at a moderate reactive series. So, aluminum can displace iron. Aluminum can displace iron, right? So, this is the reaction. Already, you got this equation in a lesson number 2 also. Lesson number 2, balancing purpose. Example number 1, calculating the atomic weights of produced substance, iron or aluminum, whatever it may be, right? So it is about a thermite reaction. Then we have third method, right? Up to now we discussed only 2 series, right? That which are available high reactivity series and the other is available at a moderate reactive series. Now we are discussing about the metals which are least reactive. What they are here? Ornament metals, including hydrogen, silver, platinum, and gold. So these are the metals which available in the least reactive series. So most of them available in a separate form. They can available in their free state, right? So just you need to separate the impurities present in them, maybe that soil particles, right? And other materials found in them very, very low reactive, right? So here they are maximum found in free state. So here oxides of these metals make maximum they are available as HCO, AgO, right? Like this. So here oxides formation, they are available in the oxide form. So you need to reduce to get crude metal from them. For example, from HCO, you need to get Hz. How it can be possible? By simple means reduction process, right? So how to reduce it? Okay, here just you need sometimes what a displacement reaction, right? From the aqueous solution, you need to displacement reaction. What they are here, if they are combining with the other elements, sometimes in least cases, right? Suppose if they are available in the sulfide form, what to do? Just you need to convert that into oxide form first. So that is what a process of roasting, right? So roasting is a process, the ore which can be heated in the presence of oxygen and converted into oxide form. So sulfide ores are used in this process. So sulfide ores in the presence of oxygen converted into oxides. The impurities will be released in the form of gas, sulfur dioxide. Further heating, what happens? What happens here? Oxides can be converted into crude metal and releases oxygen gas. So this is the simple method first, right? So here, sometimes you may require a displacement reaction from their aqueous solutions, right? In the molten state. Okay, in their aqueous solutions called the molten state of that particular ore. Suppose here, silver sulfide, AgS, right? So in this, they can use cyanide, right? Cyanide ions, Cn minus. So here Ag2S with this cyanide ion can form dicyanoargentate ion, AgCN2 minus, dicyanoargentate ion. So this is the composition of dicyanoargentate ion. Remember that is objective bit, dicyanoargentate ions, right? So here you can separate that sulfide ions, S ions, right? Then again, this dicyanoargentate ion will be added by high reactive metals like zinc. So then again, what happens? It can form ion, zinc, right? Zincate ions. So here it can form you ZnCnO, CN4, 2 minus ions, and it can displace the silver here. High reactive metal can displace least reactive metal. So zinc is high reactive comparing with the silver. So that silver will be separated. Like this also we can separate. So here simply you will get silver ice precipitate in this process. Remember these things, dicyanoargentate ion, and in this reaction the precipitate is what? Silver in the solid form. Here it is liquid form. So these are the objective bits chances. Okay, then maybe they will ask you to explain about the stages, right? So first stage is methods, physical methods, hand picking method, washing method, froth flotation, and magnetic separation. Second stage is extraction of crude metal from the ore. So in this you have three methods, three different methods. What they are here? Highly reactive, moderate reactive, and least reactive. Highly reactive, moderate reactive, least reactive. So in that also different processes we are applying. So for highly reactive metals, we are applying the electrolysis process, right? For moderate reactive, reducing process, converting them oxides, self reduction or auto reduction, thermite process, they are the important processes in them. In this, converting them into oxide form by heating, then again heating to convert that into metal form. Here this is. The next, sometimes you may depend on the displacement reaction. For example, here silver is given. So these you need to prepare well to explain about that second stage. Then what about the third stage? Refining or purification. Right? After extraction of a crude metal, it may be left with some impurities which are dissolved, combined completely. So that you need to separate them. So here this process is called purification or refining process. Purification or refining process. The metal obtained by the reduction of the ore is usually contaminated with impurities like unchanged ore. So other metals may be present in them. The quality of the crude metal decreases due to presence of these metals. So we need to decrease that percentage, lowest percentage or 0%. So we need to separate them. So how to separate them, right? So in the purification process, right, some important process methods are there, purification methods, right? Mainly we are discussing about the 4 methods here. So before going that, one example is given here with a blister copper. That formula is CuFeS2, blister copper. CuFeS2, blister copper. So that blister copper contaminated by the sulfides and iron, right? Sulfide and iron pyrites. So how to separate them, right? So here that will be separated. That will be separated by using suitable methods here. What the suitable methods are here, right? Sometimes maybe it is electrolysis process or some other processes like liquidation, distillation, falling, right? So these are the refining methods, right? So what is actually refining or purification? It is the process of obtaining the pure metal, right? It is the process of obtaining the pure metal from the impure metals, right? Obtaining the pure metal from impure metal, that process is called a refining method. So here important refining methods are given. They are namely here, simply 4 methods are given here. That 4 methods you can understand well, right? So they are the refining methods here. In these refining methods, right, mainly 4 we are discussing here: distillation, falling, liquidation, electrolysis process, right? Distillation, falling, electrolysis process. So here, what they are here, simply distillation already you learned in your 6th class. Water distillation, distilled water. What is that? Simply you are taking the liquid in a container, right? For example, conical flask, and heating that continuously to convert them into vapor form, right? Then that collected into another, right? By cooling. So in this, the technique we are used here, simply boiling point. What we used? Boiling point. So boiling point is different for the different substances. For example, water has the boiling point is 100 degrees Celsius, right? Salt, common salt, NaCl, right? Cooking salt, that has nearly 300 and above. So these techniques we can follow, right? So the metals which are available in the molten metal, impure metal, from that you are able to separate that impure metal, pure metal, impure metal. To separate them, to apply this method, what you needed first observation, what you need particularly the property of the materials. Can anybody? What the property I needed here to separate impure metal and pure metal, which are available in the same molten liquid. It has pure and impure. What the difference I needed here between pure and impure metal? That is here simply difference in their boiling points. If there is no difference in their boiling point, there is no use by heating that, right? So boiling point differences. One must be at low, one must be at high. That you need to observe first. So this method is very useful for purification of low boiling point metals like zinc and mercury, containing high boiling point metals as impurities. Or no problem, here low boiling point metals are impurities, high boiling point metals are pure metals, then that can be evaporated. So you need difference between the melting points. Then only we can apply this method. So heating continuously to extract the pure metal, right? You are heating the material continuously, that molten ore, which contains pure and impure metals in them. That metal in molten state is distilled to obtain pure metals, right? So metal is a distillate, separated a substance by the vaporization, right? So that we can collect, that called as a distillate, separated substance, right? So this is about the distillation. Is it clear? Distillation process, distillation clear? Go to quick reaction. If it is not clear, just I will know the doubt from you. Yes, clear. Right now about polling. So polling is nothing, actually we are nothing doing here, right? Simply it is also depends on something boiling point only, but here we are not particularly heating up to a particular temperature, right? Just we are using here green logs for stirring, green wooden logs for stirring. Why we are stirring continuously? Actually that pure and impure material is available in a molten state, right? It is available in the molten state. So that which is available in the molten state contains pure and impure materials, right? So here that maybe contains something gap between them if it is solidified, because that air may be, gases may be trapped in that liquid, right? That gas may be trapped. It is not a thin liquid, it is a thick liquid, not like your water, right? So it can trap the gas bubbles in it, right? The impurities are removed either as gases or they get oxidized. So sometimes that metals reacting with them and available in the form of oxides. So that can be removed by stirring continuously. So blister copper is purified in this method. Reducing gases evolved from the wood prevent the oxidation of copper. They are not allowing the material to oxidize here. They can be reduced in this process. So this is about poly. So here that impurities get maybe here oxidized. They remained as a scum called slag. So that impurity available in the liquid form called as slag here. Molten state impurities, right? Called as slag here. So that can be removed in this process, right? Reaches the surfaces that can be separated. Then about liquidation. Liquidation is nothing, converting into liquid form, right? So already it is available in the molten state. Further heating, the thickness may be reduced, right? Or it may be available in the solid form. Okay, no problem. Then what we will do here, just we can take a slopy surface. We are allowing them to flow. We are allowing them to flow on slopy surface, right? So here further heating. First, what happens, which is at low melting point, that starts to flow, blown away. Low melting point that can be separated. So here it may be taken as solid form or maybe in the thick molten state. So if you heat further, what happens? That low melting point material can be converted into liquid form first, and it can be allowed to flow on the slopy surface. So this can be separated here. This can be separated. So liquidation help you to separate the lowest or low melting point, like example is given, tin, right? So it can be melt at lower temperature comparing with the other. The next about electrolysis process. Electrolysis process is nothing. You are taking one container and arranging the electrodes in it and supplying the electricity, right, through the liquids here. Not directly. It is not connected. It is come in contact with the liquid filled in it. If it is conducting the electricity, that electrodes will supply the energy. Otherwise, that circuit remains as open circuit. So here, simply this liquid is an electrolyte. So what we can take, molten state material, right? Impure metal and pure metal we can use as anode and cathode, right? So anode and cathode will be selected based on the molten state liquid here, right? So here anode is used a strip of same kind of metal, right? Cathode also a strip of same kind of metal, but one is pure metal and the other is impure metal, right? So impure metal is anode. Remember, impure metal is anode and pure metal is used as cathode in this electrolysis process. Previously, we learned graphite rods are used as electrodes, but in this electrolysis process, electrolytic refining process, we are using that related materials only as electrodes. One is made up of pure metal and the other is made up of impure metal. So anode is impure metal, cathode is pure metal, right? Cathode is pure metal. So make it underline objective bits, right? So here, then they are added by suitable electrolyte here, which containing soluble salts of the same metal, pure and impure. For example, here in case of copper, right? In case of copper, what happened here? Simply, it contains impure metal related to the same salt, same metal salt, right? Suppose copper sulfate, copper oxide, same metal salts only, but one is in the oxide form, one is in the sulfide form, right? So that can be, or that copper metal containing copper sulfate. See here, same metal having the impurity sulfides. So we need to reduce them. So what they are doing here, one is used as pure metal and the other is used as impure metal electrode here, right? They are using electrodes. So it is electrolytic bath containing the soluble salt of the same metal. The required metal gets deposited at the cathode because here metals are positive ions, right? Positive ions. So positive ions move towards the negative terminal called cathode. So at the cathode, you are obtaining the pure material ions. So that ions can be converted into pure metal, that electrons which are released at the anode. So at the anode, that metal can be converted into positive ion, releasing the electrons. That metal can impure metal, pure metal, both are different, right? So that ions will join with, attracting these electrons and forming the metal. So at the anode, electrons will be released. At the cathode, that electrons are combining with the pure metal ion, then it will be converted into neutral atom. So this is actually happening in the electrolytic refining, right? So example, as example here, copper is given, right? Copper is given. So what you need to write the equations, just observe here, right? At the anode, positive ion formed. That positive ion moves towards the cathode by attracting the electrons. So pure metal, impure metal is there. That's why you have the difference. Both are copper, sir. How it can move? No. Here, depending on the pure metal and impure metal, it happens. So this is about electrolytic refining. Electrolytic refining. So you need to learn these 4 processes, right? That electrolytic refining process is important, right? So one more example also given in your book, that is zinc. Zinc also purified or refined in this way, right? So blister copper impure deposited at the bottom of anode, right, contains antimony, selenium as impurity, tellurium, silver, gold, platinum, etc., right? So if they are large in percentage, they are also recovered by the same electrolytic process, right? But they are available less in percentage. If you want to separate these antimony, selenium, tellurium, silver, gold, it will take much amount, more time. So economically, it is not feasible. So we cannot refine them, right? So this is about electrolytic refining. Then here we have one lab activity, that is corrosion. Metals we obtained, then that metals oxidized actually, reacting themselves with the oxygen in the presence of water. So that leads to produce metal oxides. That is only called here corrosion, right? That is only called as here corrosion. Okay, oxidation. The strength of the metals decreases and they completely decomposes, right? They completely decompose. So that process is called here corrosion process. Rusting of iron is best example for that corrosion. Rusting of iron. Not only iron, remaining materials also gets rusted. For example, copper. If you observe the copper materials, they deposit one substance which is available in the green color on them, right? For example, taps you may see, right? Copper taps, right? They get deposited with the green color substance. That is also copper oxide or copper carbonate, green color coating on them, right? The deposits are nothing. It is decomposition process, right? So here it is. Remember them and join immediately. We'll discuss the remaining topics related to this lesson. We'll complete the total syllabus today, right? So join immediately. This time completed.